MOSFET. That's the last topic for this particular unit. Okay. And this is metal oxide, metal conductor effect, field effect transistor. Okay. So that's MET MOS. So, metal oxides have been used enormously for a number of applications. Even in electronics also this plays a very important role. So certain metal oxide, depending on how they are actually what they are composed of, will actually also behave as semiconductors. Okay, so metal oxides like tin oxide or silicon dioxide or zinc oxide also behaves like semiconductors. Okay, so that's why they are metal oxide semiconductor field effect transistor. Okay, and this is what we are going to discuss today. Okay, what is the advantage? If we just write down few points here. Okay, the first point I'd like to mention is the input impedance. Okay, input impedance, in fact, for a metal oxide is even greater than that of a field effect transistor. Okay, so the input impedance of a MOSFET, okay, is much more to FET. Okay, uh, field effect transistor. Okay, uh, because it has got a very small leakage current. Okay, because I'll just explain this to you. Because of a very small gate leakage current. So usually what happens is in a metal oxide we have got a greater input impedance compared to a field effect transistor. Okay, so what I'm going to do now is I'm going to draw the figure for a metal oxide semiconductor. Okay, uh, field effect transistor. So this is actually something which is similar. It also has got a channel. It might be an N channel or a P channel. Okay, and depending on the circuit we can basically have it. Okay, so let me just draw the figure here first. Okay, and then you will see what's the exact difference between this and the field effect transistor. So what happens in a metal oxide uh, field effect transistor is we basically have got an additional metal oxide getting deposited. So this is that oxide layer that I'm talking about here. Okay, and on top of that we are actually going to have the gate part. So on top of that we are going to have the gate. So this is the difference with our field effect transistor in general. Okay, and then if I can just draw the basic part here. Okay, so we can just probably label it down. Okay, so this part is basically the substrate. This is called the substrate now. Okay, the part which is just opposite to the gate is called the substrate. This still remains the gate. This still remains the gate. Okay, and this is actually called the oxide layer. This is the oxide layer. So I will probably discuss about its importance tomorrow, but then today we are just going to look into the construction. So this is the oxide layer that we have, and this oxide layer, if it's a semiconductor, it is basically behaving like an insulator at room temperature. Okay, and this side we are actually going to have the drain. This is all the metal connection. This is a metal connection. This is a metal connection. This is how the connections are made. This is the drain. So this remains the same. Okay, and this is the source, if you remember. Okay, so this is the source. Okay, and now depending whether it's a P channel or N channel, we can have it. So basically if we have a P type here, this is basically an N channel. Okay, so this is a N channel metal oxide semiconductor field effect transistor, and this is how it usually looks. Okay, so the difference lies here. This is the difference that we have. The oxide layer is the difference. Okay, the symbol is also not very complicated. It's almost similar, but then when you draw MOSFET, you have to draw it like this. I will tell you why we basically draw it like this. Okay, the idea is simple. So that's the symbol. Okay, so this part is basically the substrate. Okay, so what I will do is, let me just complete this first. You have it like this. Okay, and then this is the substrate. Okay, and then this is the drain. It remains the same, no confusion here. The sign is almost the same, right? It's the source on this side, and depending on whether it's a p-type or an n-type, okay, you can actually have it. But this is the interesting part. Since this is an insulator, okay, because this is a metal oxide deposited here, this side is one terminal of the gate, and this is the this is the part which is actually connecting to the n channel. This is an n channel, let's say. So that means this is actually separating the gate from the channel, and that means it is acting like a capacitor, okay, because you have some kind of material inside that is acting like a dielectric. So that's why this is here. You see a gap between these two are not connected, so this is basically acting like a capacitor, and that is the entire principle of working of our metal oxide semiconductor field effect transistor. And this is why the symbol is like this, okay. So this is your symbol. So I think it's very simple, you can remember it easily. If it's a normal field effect transistor, we don't have this part, we just connect it directly, okay, because this gate will actually have a different rule, but here it plays a different role altogether, okay. We are going to look into that in the next class, okay. And this is the schematic. Okay, so what we are going to do tomorrow is, in electronics class, we are going to just look into this metal oxide semiconductor in closer detail, okay. We're just going to write down few sentences about the construction part, and depending on what potential I give on this side, I can have a positive charge or a negative charge on this end, okay. And based on this, we can actually have the working of a metal oxide FET, okay, semiconductor FET. So this is what we are going to do now. Probably I'll just give few important points on the construction, okay. So I think few important points on construction is important. Let's just write down that, okay. So whenever you're writing an answer, please make sure that you write down these important parts, okay. But please make sure that uh, this is something which I have observed, that some of you are actually writing it down the same way I'm writing it, okay. So it's like I am doing it in short because I have to finish my class. I cannot give you long sentences, but when you write down in your exam, please make sure that you actually are using full sentences, full words, okay. That is important, okay. So basically it is an n-channel MOSFET. So you have to see this first, okay. We're actually doing an n-channel MOSFET, okay. And it is basically similar to JFET, okay. Similar, might be this important, similar to JFET with few modifications. So I'll just point out the modification, and then probably it's better to understand that how does it exactly work, okay. The first point is there is only, you can see this, only one P region. So if you look into our typical field effect transistor, junction field effect transistor, this is actually having two p-type regions, okay. So this is basically called the substrate. So we have the substrate, okay. This is the one junction that we have, okay. And might be the next point would be a thin, now this is important because that is the entire working of a MOSFET, okay. A thin layer of metal oxide, okay. So what is that metal oxide? It is usually silicon dioxide, okay. Silicon dioxide. Silicon dioxide is the metal oxide that is mostly used, okay, is deposited. So there are different ways of depositing, okay, using some technique, okay. These depositions are done maybe a kind of thin film, okay, layer over layer, okay, that is done, okay, over the deposited towards the gate terminal, okay, gate terminal, okay. And then we can actually say metallic gate is deposited over the oxide layer, deposited over the oxide layer. So you have got the silicon dioxide, and then what happens is a metallic gate is basically deposited on top of that. So this is what is happening here. We're actually depositing a metallic gate on top of that, okay. So that terminal is basically the gate, okay. So SiO2 is basically a insulator, okay. And hence acts as the separation, I can say separation between the, so you know this is a separation between the N channel and the gate terminal, okay, between the N channel and the gate terminal. Please remember this, because it will basically now act as a insulator, okay, and since it is an insulator, it is also called insulated gate FET, okay, so we can just say insulated gate FET. That is the reason why it is called an insulated gate FET, okay. So this is an important point that we should remember, and this is how the construction is done. So if you just want to explain the construction part, probably you can just use these points, okay. It has 3 terminals. Now that is same, okay, similar to JFET, okay. And what are those terminals here? So this construction part remains the same, but you know the way they work are different. Source, gate and drain. Gate and drain. Okay, so this is important, and these are the construction part. I think this is something which you can easily remember. And then you draw the schematics, okay, you have to show the schematic, and you know this schematic, you see this part. This is not directly connected to the drain of the source, and this is how it works, okay. This is the insulating part that it has, okay. Let's write down some important point on its working, okay. So let's just write something on its working. So we're just going to talk about the working. Let's try to understand how it works. What I'm going to do is probably just going to write down few points here, okay, and then you can just make the sentences out of it. So working in general, I can say it's the principle that we are talking about here, okay. And you know what I can write down here is, here gate is formed as a small capacitor, is formed as small capacitor. So that's the capacitor that we have, and that is the entire principle of its working, okay. And then so we have 2 plates in a capacitor. So one plate is the gate, okay, gate, I'm using capitals, I'll use that, okay, and the other plate is the channel with metal oxide as the dielectric, okay, with the metal oxide as the dielectric, you can say. So this is one more point, okay. I'm just writing it down one below the other. You can obviously make sentences, okay. So what happens is voltage is applied to the gate, okay. Let's say voltage is applied to the gate, okay. And then what happens is if it's a negative voltage, okay, if negative, then the electrons in the N channel, now you know these N channel electrons are there, okay, which is basically an N channel electron. We are taking that example, okay. What happens is that this negative potential which is there at the gate will actually not allow the electron to go up, okay, and then it will be lesser in number. Then the electrons in the N channel is lesser in number because of repulsion, okay? So what I mean to say here is that if I'm applying a negative potential here, okay, maybe I can just draw a quick figure here, okay. So if I take this, okay, let's see if I can do it a bit fast, okay. Rub this off, okay. So what we have here is the gate, the oxide layer, okay, and everything is there. Let me just rub this off for clarity of the image, okay. Schematic also not really I'm using now, okay. So what I'm going to do now is basically just going to draw the potential that I'm going to apply, okay. So what I'm going to do is I'm going to apply a potential between the gate and the source, okay. So I'm going to apply a potential between gate and the source, and of course at the output terminal between the source and the drain. Let's take this. So this is the output terminal, and of course the substrate is also connected here. Okay. So we'll do the connections basically here at this particular point. Okay. What I'm going to do now is just draw the terminals, okay, or the potential at the two ends. So if this is an N channel, and if I'm going to apply a negative potential, I have to apply a negative potential at this particular end. Okay, so this is going to be negative. Okay, so this is there. Maybe I've taken a bit too much of gap. Okay, on the other hand, this will be again positive. Please make sure that your potentials that you apply is correctly done. Okay, so this is the potential at the output, and this is the potential at the input. Okay, now let's just get back into the statement that what voltage is applied to the gate, and if we are just considering an N channel gate, okay, N channel MOSFET, if it's negative, what happens is this gate will actually have the negative potential. So on this particular end, on this particular plate, we have got the negative potential, and in the N channel we have got the electrons which are negative, again trying to flow in this direction. Now because of this negative potential, this is going to give a repulsive effect, as a result of which it is not going to flow from this end to the other end, and because of which we are actually restricting the number of electrons. Okay, so what we have is negative, less number of is a less in number because of repulsion, and hence less electrons are available for the drain. Okay, we have that. Okay, what happens on the other hand if we are actually giving a positive potential? If, okay, let me just take a different slide. If we apply a positive potential, if we apply a positive potential on the gate plate, let me say, okay, gate plate, there will be more electrons available. Okay, so this is what is happening here. We have got more electrons now. Okay, and as a result of which we can actually control the current. Okay, so if we just write down few points here, maybe we can just write down a few points here. Okay, so the source to the drain current, okay, the source to the drain current, okay, is controlled by the electric field, okay, of capacitor formed at the gate. Okay, electric field of capacitor formed at the gate. So this is the first point. Okay, this is how it is controlled. Okay, one more point might be, unlike JFET, okay, what happens here is that the MOSFET has no gate diode. Okay, has no gate diode, so basically it does not have that property. Okay, so what we can do is, since in JFET we basically have it that the input terminal or the gate terminal should always be in reverse bias, but in this working of MOSFET, we really don't need a reverse bias at the input terminal. It depends what we need. If we need more current, we can make it positive, so we can change this battery polarity to positive. On the other hand, if we need less current, we can make it negative. So basically we don't need only one kind of potential, we can always have both the potential possible depending on what is our need. Okay, so what happens is this makes it possible, okay, with to have positive or negative gate bias, okay, gate voltage we can say. This is one more point. Okay. Number 3. Now what happens is it is basically the gate is forming a capacitor, right? So it basically will have negligible gate current that flows, okay, whether positive or negative voltage is applied, okay. So whether you apply a negative or positive voltage, you are not going to have the effect from the gate current, because you know there is an insulator in between. So you are not going to have any kind of signal from this end. So that means we can consider this to be a high input impedance device, okay. So high input impedance device, so high input impedance, as there is no gate current involved, not as, I think, and hence, since high impedance and hence there is no gate current involved. So you know this gate potential will only control this. There is no effect from this to this part, okay. There is nothing flowing from this end to this end, because there is a insulator in between, okay. So that is there. So that is why it is basically a high input impedance, okay. So what happens is the input impedance that it will have is 10,000 mega ohm, okay, to around 10 lakh mega ohm, 0, 0, 0, 0 mega ohm. So you know it has got a very high input impedance, okay, and this is the range typically, which is far greater than compared to that of a JFET. So this is what is MOSFET is all about, and this is how it works, okay. So this is where we actually complete our lecture on transistors.